Hello and welcome to TGIK. This is, oh man, it's the November 17th, so it's the week before Thanksgiving, and it's TGIK number 17, which is crazy. Not a significant milestone in and of itself, but it's definitely crazy to think that have done 17 of these things. So it's actually kind of fun, getting better at it, I think, or at least have had some ups and downs. So thanks for joining me, and welcome, Suresh. And as you folks join, feel free to say hi on the chat there. Let me know if you have any problems hearing me or seeing me or what have you. I want to make sure that I'm getting across. One of the weird things that you learn as you start doing this is that you're talking out into the void. You don't know if you're just talking to yourself or if it's actually getting out there. So I really, really like being able to get the feedback and see what people are hearing. Oh, and sorry it's so late there. Time zones are horrible. I don't know when to do it. There's no good time. But thanks for staying up late and joining me. Anthony, Federico, thank you for the happy birthday. I'll be talking about that. Yeah, oh wow, everybody's saying that. Thank you. So yeah, good to see y'all. Okay, well, oh, Keith from Scotland, awesome. And so, yeah, okay, so it's coming through, sounding good, looking good, awesome. Alex is in Atlanta, good to see you. And 6 more years, yeah, it feels like 6 years, Liz. David from Hungary, good to see you. All right, so let's start jumping in. I mean, reach out. Oh, Jose from New Zealand, good to see you again. Sebastian, awesome. So yeah, so let's go ahead and get started. Hopefully the lag's not too bad on the chat. So if you guys have questions, let me know. I try and keep an eye on it. You know, and it's a race when I make mistakes when I'm typing to see whether I'm going to notice first or if you will. Steve-O from Munich, nice to see you. So first of all, I want to show. This came up in our Slack, our internal Slack. Tomiko made this. TGI okay. I thought it was funny. It's really bad, but I wanted to show that off to folks. It made me laugh. And then there's the 1 year at Heptio. So this is a big milestone for us. We started about a year ago. I think we started putting the company together a little bit before that, but this is when we really brought things together. And so it's gone really fast. It's both fast and slow. It's crazy to see so much happen. The team that we've built is amazing, and I think back sort of like what we've accomplished. And Craig, in this blog post, it's at blog.heptio.com, goes through a bunch of the open source projects and stuff that we've done. The biggest thing for me, though, is just the team that we've built. It's a unique experience that I wasn't expecting when we did a startup. Every new person that you bring on board really brings themselves, brings their experiences, brings their time and their energy, and it really, it's both a boost to the company and also a personal boost to have people sort of join us on this journey. And yeah, so we got a lot of work ahead of us, but we also have got an awesome team, which is really great. So yeah, so here's to a year of Heptio, and there'll be many more. So yeah, so that's something that's exciting that's happening for us. Let's see. I think the gain on this thing is a little too high. Let me turn this down. Yeah, I'm seeing red bars there. Okay, there we go. Maybe a little bit better. Yeah, thank you, Jose. All right, so other stuff that I wanted to point out. There's not a lot of interesting new stuff going on in terms of new projects that I've seen this week. I think a lot of folks are saving some stuff up so that they can start talking about it around. Oh, thanks for the birthday cake. So they can start talking about it around KubeCon, because KubeCon is going to be the first week of December in Austin, and so a lot of folks are going to be there. We're working on some stuff feverishly that we're going to be showing off at KubeCon, and I'm sure a lot of other people are too. So we're going to see a whole raft of projects after KubeCon and going in through the first of the year. The one thing, though, that I thought was really cool is that Jamie Hannaford, who works at Rackspace, and I believe he's in Europe, Where's Jamie based? I think in Berlin. He's based in Berlin. He did this really cool thing of what happens when you do a kube control run of an image. Oh, Suresh, yeah, KSonnet. We're working on some KSonnet stuff. It's all in the open. It's not quite buttoned up yet. So you can, feel free to go and start, trolling around and looking at stuff. I think we're still working on making sure that we can, get all the fit and finish there and make sure that the narrative hangs together and a bunch of stuff like that. Okay, so Jamie wrote this thing which goes into excruciating detail about sort of what happens when you do a kube control run. I love these things because when I start looking at new systems, I'm a depth first learner. I really like to really understand what's going on down to some sort of bedrock. I think there's certain people who are what I call breadth first, where they're very task oriented. They want to get stuff done. They try some stuff. It looks to work. Okay, we're good. Let's go. Right? And then there's other folks who are like, I don't want to use something unless I understand how it works. And I think that a lot of systems engineers are definitely in the camp of depth first, where they really want to dig into things deep. And so one of the interview questions that I'll ask sometimes of folks is, hey, you go to a web browser and you type www.foo.com and then you hit enter, what happens next, right? And it turns out that a lot of the answers to that question really betray where people's skills are, where their knowledge base is, what is the stuff that they've done before. So for me, for example, like early in my career, I worked on Internet Explorer, so I can go into excruciating detail of what happens inside the browser, right? Most of the folks that I talk to, though, are server-side engineers. They're thinking about the network, and so they almost immediately jump to talking about hey, so these packets go out on the network. Similarly, there's folks who maybe have a hardware bent and they're like, oh, you hit enter, that's like there's a debouncing circuit in your keyboard, and let's talk about how USB and interrupts work and all that stuff. So it's kind of fascinating to actually see somebody really go through this stuff into detail. And I think, over time what happens is people go into more and more depth as they understand different parts of this. So I think this is a really cool resource. A lot of stuff going on here. It's kind of one of these things where you realize how crazy it is that computers ever work at all, but but super, super cool stuff. So thanks for putting that together, Jamie. And I'll put links to in the show notes, and I also tweeted this one out on Twitter. So with that, before I move on to sort of the main program, so today we're going to be talking about resource requests and limits and quotas, and how Kubernetes handles over-constrained, or over-committed systems. And so I've been doing a little bit of, I'm going to actually star Jamie's thing. I didn't do that, so let's boom. There we go. So as we dig into that, we're going to hit some of the limits of my knowledge here. This is one of those things where I have a pretty good high-level detail, but when we start talking about the exact sort of like fine-grained interactions of this stuff, it's not a place where I'm totally an expert on this stuff. And then, did Jamie go into initializers on here? Yeah, so initializers. This is fascinating. One of the things that I do want to call out as you read through the initializer stuff, and I think I mentioned this in a previous TGI kit, initializers are still in alpha, right? So these initializers are still in alpha, and so they're not going to be turned on in a lot of clusters. This is this stuff. And it turns out that there's some rethinking moving forward in 1.9 to actually put some of the initializer stuff on ice for now. And there's work to make sort of callable webhooks that can mutate resources as part of admission controllers. And so, you live on the bleeding edge. This stuff will almost immediately get out of date, but it's something to keep in mind. Is if you start reading about initializers and it's really interesting, it still is something that's relatively early in terms of its development life cycle. And so it's not turned on with GKE, for instance. I would love to do an episode on initializers and webhooks and admission controllers at some point and really dig into it, maybe write some code around that. I think that'd be a lot of fun. Okay. So that was Suresh saying that he liked the thing on initializers. So this, like I was going to say, this is an area that I don't have a great ton of experience in, right? Like really sort of in Kubernetes, what you find is the different areas of specialization in Kubernetes mirror a lot of the specialization that systems engineering actually goes to. You have people that go deep in storage, people that go deep in networking. The scheduling is its own thing. There's the API machinery stuff, which is like the initializers and emission control. Auth is a whole nother ball of wax. There's auth at the control plane, but then there's like security and capabilities down at the node level. Most of this stuff here that we're going to be talking about is both operating at the scheduler level, which is how do we actually figure out which jobs we want to put or which pods we want to put on which nodes. And then down at what we call SIG node, which is the kubelet and the CRI and stuff like that, the runtime, Docker, that type of stuff that's happening at the node. And that stuff, because we're really talking about a distributed system, it has its own different ways of describing things. And so as we go through this stuff, you'll see that there are two similar concepts where some of them apply to the scheduling side of the house and other of them apply to the node side of the house. So Jay Hernandez says, E2E testing is something I have no clue. Glue, you said glue, but I assume it's clue. Can you point to something about this, especially for testing operators? I don't have anything off the top of my head around E2E testing. There is the end-to-end, so this E2E is end-to-end. There are end-to-end testing for Kubernetes itself, and if you go into the Kubernetes code base, the main mono repo, you'll see a lot there. That stuff's always a work in progress. There's always work to continue to enhance those things, classify the tests, make sure that the tests are reliable as possible. So a lot of effort in the community really going towards that stuff. The other place that I would say to look for examples on how to sort of validate clusters is take a look at sort of how Sonobuoy actually packages these tests up. So Sonobuoy is our project that we started called Here We Go, and it essentially will run those end-to-end tests for you. And so this is a good place to see sort of how can we actually package this stuff up. So hopefully that'll be helpful for you. Yggdrasil. You know what? I was reading an article about what Yggdrasil is. It's a Nordic tree, mythological tree, right? I don't know. I can't pronounce it still. So you said you're hoping for news at AWS reInvent about sort of what's coming from AWS. Yeah, I think it's. I can't say anything specific there. I'm hoping that there'll be a lot of excitement around Kubernetes. We've definitely seen an uptick in terms of the amount of attention that AWS is giving Kubernetes. So I think that relationship is definitely getting more interesting, and I think everybody's sort of waiting to see what's going to happen at reInvent there. So so that should be super cool. It's the world tree. Yes, the world tree. I have to work that into a Kubernetes name someplace maybe. All right, so I'm going to go ahead and get started. A big part of this whole scheme is how do you pack more stuff in. So, okay, Tim St. Clair is the lead on Sonobuoy, and you can feel free to hit him up if you want to get some more information on sort of end-to-end tests within the context of Sonobuoy. So when people look at containers in general, things like Docker and Kubernetes and these types of systems, there's, I think, really two main reasons why they find it interesting. A big reason is the development process and concepts, right? So much of what we've been talking about is using Kubernetes as a dynamic platform for being able to deploy, visualize, and build on top of. And that's really focused at the application developer of how can you give people new concepts, new APIs, new building blocks, new toys to do interesting stuff. And so like the whole series of TGIKs that I did around serverless really is looking at systems where people are starting to build interesting things on top of Kubernetes. CI, CD, deployment systems, all that stuff really fits into that category. The other interesting thing is really an idea of how do we squeeze more out of the resources that we have? How do we make sure that we can use, every part of the cow, where the cow is your computer or your resources that you're buying? And different people actually give different amounts of weights to these different types of scenarios. And obviously, the more and more resources you're buying, the more and more important it is that you actually run that stuff as efficiently as possible. So the whole idea around scheduling means that I want to actually find, oh, I have this thing I want to run. I want to find where I want to put it, right? Where is it going to fit? And the cornerstone of this is knowing how big something is. And so when you're playing this game of Tetris of trying to actually put stuff into different nodes, knowing the size of your pieces that you're playing with the Tetris ends up being a really, really critical piece of the puzzle. And that's how this applies at the scheduling level. At the node level, there's this question of both overcommit, how do I actually sort of use resources when they're available, along with how do I make sure that we keep workloads in their lane where they're not using more resources than they're supposed to, and then using kernel features like C groups, and this is a big part of what your runtime will be doing. How do we configure the C groups so that we can minimize noisy neighbor issues? So noisy neighbor is when you have two jobs running on the same kernel or hardware or infrastructure in some ways, and when one of the workloads starts doing something, it has an impact usually around performance on the other workload, right? And so a classic example that's honestly not well controlled in Kubernetes right now is local disk. So if you have a job that takes a hard dependency on a local directory, and you go through and you start f-syncing, which is a very expensive file operation, anybody else who's depending on that local disk, including the system, right? So this is actually a problem, including the system, will have a huge performance impact because that f-sync ends up being such a disruptive type of operation that you can make. So that's an example of noisy neighbors. There's other places where it can impact you also. You can, if you're accessing a lot of memory and thrashing caches, that can actually impact the performance of other things next to you. So like Intel adds features so that you can actually start controlling which tasks actually have access to how much cache, and you can start partitioning the cache. There's different techniques for dealing with noisy neighbors with containers, things like C groups, versus when you're doing VM virtualization. So a big part of this is overcommit and noisy neighbors is why we need to do limits and stuff. So all right, so let's go ahead and get started. So the first thing that you see here is I have a cluster with three nodes in it, and actually, let's see, I have two windows here. Am I actually talking to the same? Oh, no, I'm not. Okay, different cluster. So let's see, AWS, there we go. There we go. Okay. All right, so I have a node, and can you all see this fine? Let me know if you can't. I can bump up the font. So I have a cluster with three nodes. Because we're doing something interesting here and we're going to be like really pushing this stuff to the limit, one of the things that I've done, let's see if I do that. No, if I do show labels. This is a little bit of an eye chart, but one of the things that you'll see here is that I launched these things on Amazon as M4 extra larges. So this is actually, these are, somewhat beefy nodes. Now, the other thing that I'm doing here is I'm going to be demonstrating, and we're going to be expecting this using some of the web consoles that come with Kubernetes. So if you don't have the dashboard installed, the AWS Quick Start that we did as part of Heptio does have the dashboard installed. What you can do is you can start up kube control proxy. And what kube control proxy does is it opens a local host port 8001, and that is essentially is an HTTP proxy. And this can proxy to services And so, you know, if you open this thing up, you need to go to /UI/. And if you forget the last slash, bad stuff happens. This is a built-in redirect that actually goes to the dashboard. And then what happens is an HTTP connection comes into here. It gets forwarded from your local kube control that's running that proxy to the API server, and then the API server ends up opening another connection and actually forwarding that through. It applies auth along the way, so there's a little bit of authy stuff going through here. The interesting thing to keep in mind is that this is actually an HTTP proxy. And so, and it does some other wacky stuff where it actually looks at the content and tries to rewrite URLs. I haven't seen some great documentation in terms of the guts of what kube control proxy does, but it's great for accessing things like the dashboard when it's running in the cloud and you're actually sitting on your workstation locally. So the first thing we're going to look at here is we have nodes. Let's see, it's not easy to see the master here, but we can see that the master one is 130, 11.130 is our master. So this is our master one, and then I can click on one of my worker nodes, and you can see here that I have, you know, 16 gigabytes, 15.5 gigabytes of RAM free inside the cluster, and I have 4 CPUs. And then there's a limit to the number of pods that you can actually run on a node also. Oftentimes the limit here ends up being based in sort of networking and how you've partitioned your network. But there's also, over time, you do want to limit that, because if you had too many pods there and you haven't reserved enough system space to manage that many pods, bad stuff can happen also. And so having an idea of the number of pods, and I'm sure that there are parameters on the kubelet that let you adjust some of this stuff. All right, so the first thing we're going to do, and the main reason I'm going to do this is so that we can visualize what's going on, is I'm going to install Heapster. So Heapster is a thing that goes through and talks to the kubelets, scrapes information from the kubelets about what's going on inside the pods and how much CPU and RAM and usage is going on from each of those pods. And then it actually stores that into the default, or at least the easy path is it stores that into a local InfluxDB, and then there's a Grafana dashboard that sits on top of it. Now there's some Helm charts to actually set this up, but I'm actually going to instead use the Heapster GitHub repo to actually get this installed. And so if we go to Heapster, you can go ahead and clone this, and then and so then under deploy kubeconfig, InfluxDB is the one that we're going to actually be working on. So sure, if we increase the number of pods, there's an error called disk pressure. I think in general, just the more amount of disk space that you're taking up, the more disk pressure there is. There is this idea of conditions on nodes. So if I do kube control describe node, and oftentimes it's easier to see this stuff using kube control describe versus the UI. You'll see that there's conditions here, and there's things like out of disk, like if you actually run out of disk, memory pressure, disk pressure. And I believe, and maybe Tim knows, I think disk pressure, it might be based on I/O or it might be based on space. I'm really not sure, to be honest. But that's actually a good thing to look at. And so there's conditions here, and you can say, hey, I want to run my job even though we're out of disk space, or hey, this thing's out of disk space, so stop scheduling stuff there. So there's ways, this is essentially the feedback mechanism from the node or from the kubelet about what's actually going on. Tim has its space. I don't think there's anything built in right now about disk activity or block I/O, C group type of stuff that hasn't been plumbed through the kubelet yet. It's actually really, it's more complicated than it might first appear to be able to actually, the amount of disk activity capacity that you have is a really sort of squishy subject, and so it's really a difficult thing to control from a noisy neighbor point of view. But we're getting a little bit in the weeds there. So yeah, so we're going to install Heapster, and so you can see there's Heapster, Influx, DB, and Grafana. There's also an RBAC rules that you can use here too, to actually give Heapster the access that it needs to be able to do. I've gone through and I've modified these a little bit. What I've done here, and I'll show you my modifications, is I've added a toleration and a node selector because I want to make sure that all the Heapster stuff runs on the master. And I've done this mostly just to make sure that Heapster doesn't fall over if we start pushing things really hard. So I just want to isolate that onto the master node. So I've done that to Grafana and Heapster and InfluxDB. The other thing I've done here is I've set metric resolution on the Heapster instance to 30 seconds, which means it's going to pull a little bit faster. By default, this is 60 seconds. I set this to 30 seconds. You generally want this to be twice the essentially collection interval that's happening at the kubelet. The kubelet actually by default operates at 15 seconds. If I had more time, I might have set it up such that the kubelet was working at, like, say, 5 seconds and this was working at 10 seconds. Currently, reconfiguring kubelets is a pretty manual process. One of the things that's going to be happening over the next couple of versions is this switch to a thing called component config, where instead of configuring kubelet by, like, mucking with command line flags and systemd on every node, you can start doing this stuff on using, like, config map or config map-like files to be able to distribute that configuration to the kubelets. So we're moving the configuration of the kubelet from local machine to the cluster. All right, so we're going to go ahead and install this stuff. So let's do cd heapster deploy kubeconfig kube control apply -f influx, the InfluxDB one and the RBAC one. All right. So now if I go back here and I switch to my kube system namespace and look at all the pods, what you can see is that we now have, like, Heapster, and it's running on 10.11.130, which is our master node. So that's great. Now, one of the things is that there is interaction between the dashboard and Heapster, which is really cool. But if the dashboard comes up first before Heapster, it takes a little while before it to notice, hey, look, there's Heapster around. Before you had to, like, manually restart the dashboard, now it does a check once in a while just to make sure that that everything's running. We're going to hurry that up by actually going through and killing the dashboard pod. So I go ahead and I kill this. Now the dashboard's like, whoa, I'm not here. Let's see. But then it gets relaunched. It comes back. Now if I think I should, oh man, it didn't work. It didn't work. Pods, no, I didn't get the thing. So maybe okay, it takes a little while for Heapster to warm up. So let's go ahead and let's kill the dashboard again and see if it. And we'll look at nodes, pods, system. All right, well, we'll give it a second and it should come back. It should actually get that stuff figured out. Now, the other thing that we're going to do here is, and I'm going to look at my cheat sheet notes here, is you can get access using that same proxy mechanism to the Grafana dashboard that we're running. So let's go ahead and bring up the Grafana dashboard for Heapster. And there we go. And we can go through and we can say, I want to look at it for my cluster. And, okay, it's still scraping, so it's still figuring stuff out. And I tried this on another cluster right before this, and it worked just fine. So we'll give it a few seconds to get its act together. Did anybody see, did I do any mistakes? Did I make any mistakes? We got the role binding. We got everything running. It's actually running, right? Everything looks to be healthy here. It takes it a minute or two for it to actually, there we go. Okay, so we have some stuff coming in. We'll give it a few seconds. Yeah, we'll give it a few seconds to actually sort of get its act together. And yeah, so that's the first thing that we're going to do. And what this is going to do is it's going to actually show sort of, which pods are using how much RAM, how much memory, that type of thing, which is really, really a big part of it. All right, well, that's warming up. I want to talk about a little bit of a different topic here. And there's this idea around requests versus limits and compressible versus incompressible types of resources. And so here's a web page that you can go and look at it, and I'll put all the links to this stuff in a gist. So basically, there's two types of resources that people typically track right now with Kubernetes, and that's CPU usage and RAM. Over time, we're going to see that there'll be other types of resources that will be added on here. There's a whole working group on this stuff, or I believe it's a working group or SIG, but there's a group of people who are working on expanding this to new types of things that we want to be able to control. So this isn't sort of like a fixed set of things that we're working with here. In some ways, there's two sort of main types of resources, and folks will call these compressible and incompressible. CPU is compressible, right? You can always, to some degree, at some limit, you can always squeeze more in. You can always press more in there. It's kind of like a gas, right? You can always increase the pressure, put more in there. What means is that everything will run slower, or at least some stuff will run slower. But if things don't quite work out, you can kind of fudge things around to actually make stuff work. And then the other type of resource is incompressible, and RAMs, that is really incompressible, at least the way that Kubernetes uses it. And what that means is that if somebody asks for RAM and you can't give it to them, there's really nothing else to do. You really need to have that resource available. Now, that's not quite true, because you have this idea of swap space where you can have slow RAM and you can page stuff out. But generally, if you're running any sort of service, any sort of service or server type workload, the behavior that you get when you actually start swapping to disk is so much slower that it's really a pretty large step function, to the point where you get a lot of essentially non-linear sort of unexpected behavior when that stuff starts happening. So in general, the kubelet at this point, I think, warns and eventually will error out if you try and run it with swap turned on. Then Tim says there's other non-fungible resources like GPUs, but they're sort of like treated as whole units. It's a little bit more of a scheduler thing versus something that's actually going to impact the C group definition. And we can talk about some of the quota stuff in a little bit too. Got a lot to cover, man. There's more here than I thought. Okay, so let's see if this thing is up and running yet. Man, I am disappointed. Okay, so we got some graphs in Grafana, and then let's kill the dashboard one last time to see if it gets its act together. Error, EOF. Yeah, okay. So when the dashboard can actually find Heapster, you're going to find that you get like some nice graphs here. And then when we start looking at pods, you actually get these little things where you can see here's how much the pod is actually using, with a little bit of history around that stuff. So this is going to be important stuff here. And this is, let me see if I can make it a little bit bigger there so we can actually see what's going on. Okay. So now we got Grafana, pods, we're talking about this. Okay, now when you specify a pod, you can specify across, the basic things here, and obviously you can get more fancy with things like GPUs, but the basic things are CPU and memory, and you can specify requests and limits. So requests are, I want to make sure I have at least X amount available, right? Limits are, make sure I have, if I try and use more than X, go ahead and have me killed. So Suresh says, how does cAdvisor play a role with Heapster and Grafana? So it used to be, and maybe Tim has more up-to-date information here. My understanding is that cAdvisor used to be a separate component that you would run next to the kubelet. And it would actually then go through and talk to your runtime, whether it be Docker or what have you, to actually collect this information and publish it out. It's become such an integral part of the system as we look at things like horizontal pod autoscaling that I believe at this point, Heapster has essentially been merged. I mean, CAdvisor has been merged to some degree into the kubelet. So the kubelet now plays that role directly. I believe that's where we're at. And so that's the relationship there. So I think CAdvisor at this point has kind of been sort of eaten by the kubelet. Okay, so yeah, so there's requests and limits. Requests are you're guaranteed to get that much of that resource. And then limits are essentially hard limits of if you hit this limit, you're going to go ahead and get killed. And you can set both of these things, and you get different behavior when you go ahead and set the request below the limit. If you set a limit but you don't set a request, then they assume that your request equals that limit. And roughly what happens is you get 3 different modes of behavior depending on how you set this stuff up. And generally, like, this is called quality of service at the kubelet level. And so there's a good blog post that I'm going to link to here. Let me pull that up. This is from Nilesh. I hadn't seen this before, but as I was doing some research before this episode, I started looking at this, where he goes into some of this stuff around compressible versus non-compressible. But generally, there's 3 different levels of this stuff. There's guaranteed, burstable, and best effort. Now, when you specify, and this is what happens by default, when you specify I want to run a job and you don't set any limits or any requests, that's essentially best effort. The cluster says, we're going to do our best, right? We're going to try and make sure we don't run too many things on the same node, but there's really not a lot of feedback, and it's easy to get yourself in trouble. So this is great for development, it's great for playing around, but the truth of the matter is that if you're going to be running a production cluster, you really want to make sure that everybody is setting resources on everything. And we'll talk about sort of how you can help that process with both quotas and this way to actually default in the resources that you have. It's an admission controller. So burstable means that you have a guaranteed minimum that you're using, but you can actually start using more, and you can use that. That's when the request and the limit are different. That gap there is your room to burst, and you're not guaranteed to always have that. Burstable makes more sense from a CPU point of view. From a RAM point of view, it's very dangerous. If you're unless you have a very smart workload that actually can handle this stuff and you can handle getting restarted. But generally, if you're using more RAM than and the system needs to reclaim that for a higher priority thing or for something that it wants to be able to guarantee, you will get killed, right? You will get killed because there's no way to grab that RAM back short of actually killing the pod. And we'll demonstrate that in a second. With CPU, it's very easy. You just throttle it back. The thing runs slower. And then finally, if you set limits for everything and the limits match the request, then you're guaranteed. That means that you have a footprint in terms of CPU and RAM. You're going to get that. Nobody else is going to interfere with you, and you won't be killed as long as you actually stay under that limit. Do you know of any way to audit a cluster ensuring everything has requests and limits? That's a really good point, Eli. I believe, I don't know anything off the top of my head of a resource to be able to do with that. That's the, that type of advice and best practices is the type of thing that Heptio honestly is looking at being able to do to really guide people towards sort of best practices with this stuff. One of the things, and I didn't get a chance to actually play with this and verify this before the TGIK, so maybe we'll have a chance to get into it. If you set a quota on a namespace, doing that actually guarantees that all new work coming into that actually has resource limits on it. At least resource requests, I believe, is what it guarantees. But if you want to say, hey, I want to make sure that everything actually has limits equal to requests, that's a different beast entirely. I don't know of anything right now that will help you audit that. But it's all together, especially as we start looking at things like initializers and these mutable webhooks. You should be able to actually go through and maybe say reject any changes that actually move you out of that state. So that's the type of thing. This is why admission controller webhooks are really so interesting, is that you can implement that type of policy in an extensible way. All right, so let's go through and let's start up some jobs. So what I have here is I have a best effort QRD where I'm going to run 5 of these things. I'll say QRD is my Kubernetes up and running demo application. That's something I wrote for the Kubernetes up and running book. And so now whenever I need to actually demonstrate like playing with Kubernetes, this is my go-to utility. So we'll go through and we'll kube control apply -f QRD best effort.yaml. Okay, so this is going to get up and running. And oh, one of the things that I did here is I want to actually, just to make it more predictable, I actually have a node selector of type test. And so I didn't set any of my nodes to actually have that label. And so, you know, I don't know if you've seen this error before, but essentially what you see, yeah, I was going to talk about quota and limit ranges for a pod. Tim's talking about that. Is that you're saying no nodes are available that match all of the predicates, node selector, and you know, pod tolerates node taint. So like we can't find any nodes to actually put this thing on. So we need to actually take one of our nodes and actually add that label to it. So let's do that. Kube control get nodes, and we'll take, let's say, 2714. Kube control label node. Oh, misspelled node. Typing too fast for my own good. And we're going to do, what did I have? I had type equals test. All right, so now I went ahead and I set that, and now this actually will demonstrate sort of the self-healing nature of Kubernetes. I did this stuff in the wrong order, but eventually Kubernetes kind of figures itself out and actually gets its act together. This is the theory, at least. Sometimes it takes it a few minutes because it doesn't want to continue to slam things. See that? Okay, that thing is labeled. No. Did I screw something up, Tim? Did you see me screw anything up? Kube control get pods. Let's grab one of these. Kube control describe pod. It's pending. No nodes are available. Node selectors type equals test. And then what did I label? Type equals test. That should work. There we go. Okay, it just took it a few seconds to actually get its act together. So one of the things when I did this describe here, and this is something that doesn't show up in the UI, unfortunately, and I don't know, like, is there a way to get the raw YAML for this thing from here? I don't see it. But one of the things that if you look in the kube control describe, you'll see that it actually lists that quas class here. So this is best effort. And so yeah, okay. So we're good to go there. We now have our stuff up and running. Now one of the problems here is that I have 5 of these things. I want to start talking to them. I could try and do the proxy thing that we're talking about here, but then you do a service when you go ahead. Okay, if I do, Eric's saying if I hit the edit button. Okay, yeah, that pops me into the YAML, so you can actually see that. It's both an edit and view of the YAML. So cool. Yeah. All right, so where was I? Okay, so I want to talk to these things. I could put a service in front of these things and then use the proxy to do it. Turns out QRD doesn't handle the proxy well, but even if it did, that's not necessarily what we want because we would get a random one of these things each time. And for the purposes of this, we want to actually really go ahead and start mucking with it. There's this other command called port forward, kube control port forward, which creates a dumber tunnel. It's not a HTTP tunnel. It's a simple TCP tunnel to a pod. But the problem is that the naming of our pods is actually really non-deterministic because they're driven by deployments. And so what I did is I wrote a little shell script, and it's really dumb, and it's called this report forward, and it works in a loop where it runs one kube control command to actually list things based on a label, grab the name of the first pod out of there, port forward to that. Right now I hard-coded port forward into 8080 for QRD, and then sleeps 2 seconds and then kills it and starts it over again. And so you may see that some of my connections fail while it's doing that restart, but what this means is that if a pod gets killed and something else up, I'll always have sort of an up-to-date one running. So at least something pointing to one of those. So I'm going to go through and forward. So we have a QuarD best effort 8080. So that says I want to like continue. Okay, and we'll run this in the background. I want to keep a tunnel open to the first in the list of my QuarD backend instances from port 8080 to port 8080. That's essentially what I'm saying here. So now if I go through here and I do localhost 8080, I get QuarD. We can see it's our best effort version of QuarD. Now, one of the things I did yesterday is I added a new tab to QuarD, which actually shows us the amount of memory that we're using. And right now, it's pretty efficient. It only takes 3 megabytes. That's not bad. But I can actually make it take more memory. So let's, that's, okay. So sometimes we'll see that that lightning bolt means that one of the requests failed to the thing. And sometimes it works. Okay, so I just allocated a gigabyte of memory with this thing. And it actually is using that memory. And so these are the heap and the stack in use and stuff like this. This is all sort of Golang-y sort of heap stuff. And then I can go through and if I look at this, and it takes, remember we have a 30-second scrape on this thing. It takes 30 seconds before a delay before we actually start seeing it show up in the dashboard here. But now I have that pod eventually will get its act together, and we'll see that I actually added a gigabyte to the working set of that. Similarly, in the node that we're dealing with here is 2714. We can go to the Grafana dashboard and look at this stuff. And what we want to look at is memory usage for this node. And I can go ahead and hit View, and you can see that Grafana is letting us know, and we'll actually just look at the last 15 minutes here. We've seen that the top of the line here is the amount being used, and then they're sort of used and working set. And honestly, off the top of my head, the difference between those I'm not super clear on. Maybe Tim does. But then there's also limit and request, and so that's the sum of all the pods that are actually on that node, what their limit is, what their request is. And because everything's best effort right now, the limit and the request are at 0. But we're actually using a bunch of stuff here. Now, one of the things that we can look at here is if I go ahead and if I hit this thing, okay, now you can see it's at a gigabyte, and then I click through to the node, we'll actually see the sum across that entire node being drawn from the, this is memory usage, drawn from Heapster. So both the Grafana chart here that I have and the dashboard are drawing their information from the same source. And then if I look at it, there's these cool circle graphs here. These are essentially sort of how much is allocated, what the request and the limit totals are. These things can be computed whether you're running Heapster or not. If you want to see the actual usage of what's actually happening on the ground, you need to be running Heapster. And you can see like we don't have any memory requests or limits, so nothing exciting is happening here. But you can see that we have like about 15 gigabytes on this machine. So this is actually a pretty beefy machine. Let's see what happens if I go through and increase the amount of RAM that I'm using. Let's see, is this working? Why is that not working? Come on. You know, my 2-second thing is probably too aggressive on my kill the tunnel and recreate it. Let's change that to 10 seconds. And all right, so now, okay, now we're not going to see that error as much. All right, so we're using a lot of RAM, man. This is a really, well, I don't know why I actually got the error. Oh, maybe that was my 10-second thing restarting it. We're using a lot of RAM. I just made it do 500 megabytes at a time. I could have done a gig at a time or let you fill something in the form, but I just hacked this together pretty quick. So this thing's using a lot of RAM. And at some point, let's see, so let's wait for it to catch up here. yeah, you can see, okay, it's seeing 11.2 gigabytes at the last sample. Still nothing going on here, but you can actually go through and see, hey, look, 5.5 gigabytes going on there. I hit refresh. Let's see. It's similarly, if I do a refresh here, yeah, we're definitely using. Okay, so we're getting close to the limit in terms of the amount of memory that can fit onto this machine. So the question is, what happens if I keep pressing this button? Oh, did you see that? Heap alloc went back down to 0. So what happened there is I tried to allocate too much memory, and the program probably crashed. I'm actually not exactly sure what happened here, believe it or not. But if we go through, let's take the name of this pod, and if we do kube control describe pod and then this thing, what you'll see here is we can see the history of like, okay, this thing started at this time. The last date it got terminated with an error. 137 is the exit code. Anything over 128 is actually the signal that got sent to the thing. I think so. I believe this means that it got kill-9. I think it was a crash because it tried to allocate memory and Go, when you try and allocate memory and there's no memory to be had, ends up just crashing. But this is one of those places where debugging this is actually not as clear as it needs to be. We can do kube control logs this thing. Oh, not 137 we wanted to grab. This is the new version of it. I think if you give it a -p, you get the previous version. There you can see all my sort of like alloc more stuff. But at the end, you can just see that we do the post to actually alloc more stuff, and then the thing crashes. So I'm not sure exactly who's killing it there, whether it's the program crashing or whether there's some sort of C group type of thing that's actually terminating it, believe it or not. It's not the killer. So in Linux, there's this thing that actually says, hey, I don't have enough memory to do everything I need to do. I need to go off and kill something. Who should I kill? That's the killer. And it works with C groups to actually make sure that there's enough sort of there's enough capacity to actually satisfy the C groups. That's not what happened here. You get a different error when you do that, and that's something that we'll go ahead and we'll see next. But, so when you do best effort, at some point you can use up all the memory on the machine and nothing's going to stop you from doing that. Now let's go through and let's start some burstable ones here. And what I'm going to do is I'm going to actually say, let's start a bunch of these things. Each of them is going to request 1 gigabyte of memory, but there's no limit. Right? And let's try and run 15 of these things. Okay? And these things are all going to be targeted to that one node. So kube control apply -f resources burst. So I'm going to go through and I'm going to create a bunch of burstable ones. And what we're going to see here, if we look at it now, we've gotten something very interesting. Now you can see that the requests are adding up, and we've asked for 15 gigabytes worth of requests. So we were actually running 15 of these things. They all actually fit. And they're busy coming up right now. And some of them are, it takes a little while for the kubelet to synchronize and start everything that it's starting. But it looks like everything is actually coming up. Yeah, so these things are coming up. And each of these things is very small, not taking a bunch of RAM. So no biggie there. Okay, so that's great. This one, we have one that's pending. Why is it pending? Okay, there we go. So now they're all up and running. Okay, so the next thing I'm going to do is like, okay, that was 15. What happens if I do 16 here? If I go through and I do that, and then I run this, what you're going to see, oh, we're looking at the node, but if we look at the deployment for this, oh, look, it says, like, I'm sorry, we can't fit any more onto that because we don't have the node, like what the scheduler does is it says, okay, I want to fit this thing in. I'm playing the game of Tetris, and I can't schedule on some nodes because of taints. That's the master node. I can't, I have a node selector where I want to only schedule on a node with a particular label. I can't do that. on all except, so we narrowed it down to one node, but that one node is full, and so you'll actually get an error like this where you see insufficient memory. And so we can go in and we can look at this, and we can look at this guy, and this guy's never going to schedule because we just don't have enough memory to be able to do it. Now Suresh is asking apply versus create. How do they differ? So apply is, man, this is like way more complicated than it needs to be. And this is something that is one of my pet peeves. Create will error out if something already exists. So you can do create and then update. And so apply is really sort of an upsert where it's like create it if it doesn't exist. If it does exist, update it to the latest thing. So that's the way to think about it. Now the other thing that apply does is if you have multiple things editing the same resource, and the best example here is the replica count. Let's say that I went through and brought something up and I said replicas equals 5, and then I use an imperative command like cube control scale to say, no, I want replicas to equal to 10. When I do the apply, it actually has enough smarts to kind of do a three-way merge where it doesn't undo the cube control scale. And so whereas as update will just sort of splat things in there, apply tries to be very careful not to undo work that has been done by other actors. It's really critical when you start using horizontal pod autoscaler because it's now you have both your description for the deployment or the replica set, and then you have the autoscaler who's also mucking with that. So you have two things trying to act on the same object, and apply helps you be smart to make sure that you don't whack the work that the autoscaler is doing. Joe says, with running many websites on monolithic LAMP servers, you can easily share CPU and mem since most sites don't peak at the same time. Yeah, so what you saw here is that you can have guarantees and limits. I don't believe there's a lot of support right now for essentially, let's see, I think, Tim, you can answer this. I think the limit, you're only guaranteed your guarantee, but you can overcommit on the limit. So let's go ahead and actually try that a little bit, and we'll give that a try. And so let's go through, and we're going to change this thing. We're going to go back down to 15. Each request is going to have, each one is going to have a request of 1 gigabyte, but we're going to have a limit of memory of 2 gigabytes, okay? Or actually, let's do that, okay. So now if I go through, and I'm going to apply this, error validating limits. There we go. Now if I go through and I look at this, where are we at? Oh, internal error because I'm looking at the wrong thing. Replica sets. Okay, and this thing is busy sort of turning the other ones down and doing an update with the new thing because to change these limits you have to recreate the pods. So we'll look at the deployments. And it's busy actually bringing up the new things, what's going on here. So we have the old replica set is being scaled down while the new replica set is being scaled up. Did I screw something up here? Or burst? Oh, container. Okay, I copied and paste error. But that shouldn't matter there, so we'll just give it a second to do its thing. So this is the deployment doing its thing. It takes a little while to sort of try and be responsible as it actually restarts those 15 different pods. Let's go through and let's hurry that up, and we can go through and we can delete this thing. And then we'll go through and we'll do an apply again. Okay, so we're getting an error here. Insufficient memory. Did I screw something up? Am I misunderstanding something? Let's go through and look. Yeah, so what you have here is we have, what it says is that we're overcommitted on our limit, but our requests are at 14 gigabytes. So why is this? Oh, I think it's just still catching up to some of the, yeah, so everything is catching up here. And the best effort ones are still running, but what you're going to find here is that these guys will have limited ability to actually go through and use a lot of RAM because a lot of that other stuff is guaranteed by the rest of the cluster, right? So now, see, I'm jumping around here a little bit. Sorry about that. Okay, so now we have the burst one up and running. It's running fine. You can see that it's all using a minimal amount of memory. When I go and I look at the node that all of these things are running on, so let's look at the node, you'll see that we're overcommitting, right? So our requests are 15 gigabytes, but our limits are 30 gigabytes. And so the minimum is what you're guaranteed. The limit is what's going to happen when you get killed. So this is actually a dangerous place to run because if I go through and I start using that memory, there's a good chance that somebody else will come along and the system will need to reclaim it, and the only way it can reclaim it is by killing one of my pods. So again, like you were saying, like, hey, a lot of times not everybody's using all the RAM or all the CPU at the same time. That's true, but what if they do, right? And if they do, then you're in a bad situation because there's no way to actually sort of make the numbers work. This burstable idea works a heck of a lot better with CPU than it does with memory. Let's see. So there we go. So that's allocated resources there. We got that up and running. One of the things now we can go here. We're still on our best effort thing. I bet you if I go through, okay, I just allocated 500 megabytes. If I do more, at some point, so I can still allocate a lot of this memory. But if the time comes when the system needs to reclaim stuff, I'm not guaranteed any of this. And so to actually sort of like, I'm essentially the last in line for this memory, so I'm very likely going to actually be killed if somebody else needs this memory on this machine. Now let me go ahead and start up a different forwarder. Let's see. Oh, okay, yeah, and we're going to do quar d burst 8081. Okay, so we're going to actually talk to one of those guys. Localhost 8081. Okay, we can see this is a burst instance. We're going to hit some memory, and let's go. And okay, so this guy's using 1.5 gigabytes now. That's what we would expect. If I push it over 2 gigabytes, I get restarted. Right? So this is what I would expect. I set my limit at 2 gigabytes. If I use more than 2 gigabytes, bad things happen, and I go ahead and I get killed. And so let's go through, and we can actually look to see what does the error look like. Cube control, describe pod, blah. And what you'll see here is, oh, the last state was terminated. The reason was the killer. Because what happens is there was RAM on the machine, but there wasn't RAM for me on the machine because of the limit. And so I went ahead and got killed, and you'll see that the restart count actually ends up increasing there. So that's the basics around sort of limits. And then you can do all the same stuff with CPU. It's a little bit trickier to demonstrate just because you get throttled and it's harder to sort of visualize that. One of the things is that when you specify CPU, you specify it in terms of fractions of a core. And a core is a logical core. So if you're on a hyper-threaded machine with hyper-threading turned on, it'll be that. So it's essentially one of the things that you see in proc CPU. And it's important to realize that if you're running a heterogeneous cluster, not all cores are created equal, but Kubernetes doesn't actually know how to adjust for, hey, well, this machine has really weak cores and this machine has really strong cores. How do I actually go ahead and make sure that I even that stuff out? That's not something that's built into the Kubernetes scheduler right now. So, Somya, I'm sorry. How does multiprocessor stuff get scheduled on Kates? Yeah, you can just allocate more than one core, and it'll go ahead and get scheduled. And it's up to the container runtime if it wants to be smart about making sure that like, let's say that you request 2 CPUs. Do those things get buddied up on 2 hyperthreads that actually share a same physical core? And so understanding the topology of the machine that you're running on, and whether you want to actually sort of like lock things onto onto two hyperthreads on a core, or if you're running in something that's a semi-NUMA type of architecture, you might want to make sure that, hey, we want jobs not to span sockets. And so I don't think that any of the container runtimes currently do that. This is something that Borg does inside of Google, is it tries to be smart about how things get scheduled across different sockets, across hyperthreads and cores to really drive the best use of cache and memory bandwidth. I think, is that what you're asking for? I think that might be what you're asking there. All right. So there we go. There's that. Now, if we go through, and I haven't had a chance to do this yet, but let's go through and create yet a new thing here. We're going to do copy quard burst to quard guaranteed. We'll just call it G, because that's easier to type. And then let's go through and modify this. And we're going to do G. There's probably... Okay. And what we're going to do for guaranteed is we're just going to remove the request. And when you only set a limit, then the limit is also your request. Okay. So this means that this thing's going to use 2 gigabytes, and it's only ever going to use 2 gigabytes. It gives you things as predictable as possible. So when you're running production workloads where you really want to have predictable latency, you want to be running in this mode where you essentially are guaranteed to actually get your limit. Okay, so this is the gazillion-dollar question. How do you set same limits? Yeah, so right now the best thing to do is to monitor and actually sort of tune your limits over time based on what makes sense. A lot of people have talked about building systems that look at history and actually predict limits based on the history of a particular job, or adjust those limits over time based on the behavior that you've seen for any particular set of deployment or replica set. That's not something that I've seen anybody build a system that's widely deployed yet. I'm sure there's folks playing with it. It's not something that I've seen sort of really catch on yet. It's going to be a big deal because setting these limits is actually really difficult to get right. I think typically people tend to just say, I don't know, 2 gigabytes, right? I mean, it's so easy to do that. And so right-sizing these things is actually going to be critical. Now, one of the interesting things is that one of the things that Borg supports is dynamically resizing containers without restarting the container. So you can actually walk up to Borg and say, hey, I want to start giving this thing more RAM. If there happens to be enough capacity in that node, it'll happen in place. Same thing with CPU, without having to actually restart the task. That's not something that the kubelet or a lot of the runtimes that the kubelet depends on support right now. So a lot of times people will call this vertical pod autoscaling. Right? So horizontal is adding more, vertical is adding more to, or adjusting that limit. And so if somebody were going to do that sort of that vertical autoscaling or that resource setting, you'd have to trade off the disruption of restarting stuff to be able to adjust these limits, the chance that you get it wrong and it's too low and then something gets killed or it gets throttled, against the efficiency gains that you're looking to get here. Now we do have concepts like disruption budgets, which is like how much can we actually kill things to optimize the cluster. So there's concepts like that we can play into, but I don't think anybody's really built a comprehensive system yet to dynamically set those things. I think the first step there, and this is something that I'd be interested in seeing, is collecting enough data such that you can give people advice, right? So maybe you're not dynamically setting it while the thing's running, but you can ask like, hey, based on this task, in the history for things with this label, what do you think would be a good thing? And I think we can probably build an advisory system before we could actually build sort of a super automatic system. Okay, so now we're setting the limit here. We have 15 of these things. We know that's not going to fit. Let's just get ourselves back down to 5. I'm going to go ahead and I'm going to delete the burst ones, and we're going to apply the guaranteed ones. What did I do wrong? quard-g. Oh, I'm already in the directory. Okay, I'll delete. Give that a second. So we can do a refresh of this thing and see what we got. Yeah, you can see this stuff is bouncing all over the place. And there you can see the requests, and down here we're actually seeing the working set, and then up here is the limit. And you can see how we're overcommitted there. Okay, so now if I refresh the page that has my, my node, now you can see that our requests and limits are the same. We're not overcommitting. These things are lined up. If I go through and let's look at one of the nodes that's running here, like say this guy here, let's do a kube control describe on that. And you'll see, oh wait, this is still quos class burstable. It shouldn't be. Oh, I have to, okay, to move to guaranteed, you have to actually set the limit for both CPU and RAM. So let's go ahead and do that. And we'll give this thing 200 millicPUs. So the way when you set these limits for CPU, you can do it on percent. You essentially do it on percentages of a CPU. The unit that we're using here is a millicPU, right? So there's 1,000 of these things in a CPU, and it just makes it easier to deal with the numbers versus typing fractions in. I believe you might even be able to take 0.2% here too. I'm not sure, but generally you just say 200 millicPUs. So kube control delete deployment, or actually we'll do dash f or d, and then we'll delete that and recreate it just to make it apply. All right. Well, of course, that's not going to work. We're going to look at the nodes again. I think this is the node that we picked, isn't it? Yeah. That we've been playing with. This thing. Now you can actually see that we have requests and limits for CPU also. So we have relatively... But this will actually throttle now. So like it will not let me take more than 0.2 as CPU. And the big reason that you're going to want to set hard limits on CPU also is, again, for predictability. One of the things that Google found is that if you let people burst CPU, sometimes things will work and your latencies will be great. And then at 2 a.m., something else will get scheduled into the cluster. It'll start using a bunch of CPU. And then all of a sudden your latencies go through the roof and you start timing out on stuff and your whole service goes down and you get paged at 3 a.m. Right? So you really want to make sure that you set limits equal to, you do this guaranteed if you don't want to get paged. But if you are really worried about efficiency, like that WordPress example where you want to run a gazillion things and you want to actually sort of let it come out on the wash because they're all really small and nobody's going to use all the CPU all at once, then you can actually go to that burstable mode. But you got to know in the back of your head that there's a chance at some point that somebody may come in there and start using all the CPU and actually start causing other things to get throttled, right? And so that may actually wake you up at 3 a.m. if you run in that type of mode. Okay, so here we have this thing running. Let's go ahead and we'll do a describe on this. And here you can see quos class equals guaranteed. So that's what we want to actually see there. Now let's go through and let's open a thing there. So instead of report forward to the burst one, oh, let me kill that one. Oh, I'm in the wrong directory. All right, so I'll run that in the background there too. So now my 8081 one should be going to my guaranteed guy. Maybe. There we go. Okay. So we can see we're on one of the guaranteed guys, and I can add memory here, and I'm sure that it'll work. And I can be sure that nobody else running on this thing will actually come in and start mucking with my stuff and cause me to actually get killed for using too much RAM. But if I do use too much RAM, and the system can no longer have that guarantee, and let's see if I do this again. Yeah, so I went ahead and I got killed, and you see this thing got restarted. And then if we go and we look at the describe, you'll see that the killer is the one that killed us again here. So that's resources and limits. We're running out of time. I did want to get to quota, and I wanted to cover a couple other topics here quickly that are related to this. So the first one is that there's this idea of pod priority and preemption. Again, here we've been talking about what happens when you oversubscribe. How do you provide guarantees on a per node basis? Now the question is, how do you do this writ large across your cluster? And so this is an alpha feature now. I haven't had a chance to play with it, but I'll pull up the docs here. Essentially what you can do is you can say, we have priority classes. And these priority classes, you essentially map a value in an integer to a name. And then when people actually schedule stuff, they actually specify the priority class name. Say, hey, I'm going to be using high priority for this thing. And if you want to schedule a high priority thing, it'll actually kick out, deschedule, kill, and make room for you by kicking out lower priority things. And so this is a way that you can, the more and more we do this, you can say, hey, anybody can run low priority stuff on our cluster, but I want to make sure my production workloads are running high priority. And when it comes time to schedule those things, they're really going to be first in line to the point where they'll actually kick other workloads off the cluster. Again, this is still an alpha, so there's instructions on this page on how to actually turn this thing on. It could change. People are still figuring it out. But this is one other type of sort of how do you do overcommit? How do you actually deal with shoving more stuff into a cluster than you might think otherwise. And so this is it tries to evict things. There's another feature that has been talked about and in development for a long time, and it's this thing called a rescheduler. I don't have a pointer to that. And this is something that looks at the cluster and says, hey, maybe if I threw all the Lego pieces up in the air and rejiggered them a little bit, I could actually pack the cluster even tighter. And so it's the type of thing that'll look at the status of the cluster and says, hey, if I kill this pod and this pod and this pod and reschedule them this way, all of a sudden I get a lot more room and I can actually make more stuff schedule. So it's trading off disruption of actually killing and restarting things against being able to pack more stuff into your cluster. And again, all this stuff at the baseline is being able to describe how big are my different pieces that I'm packing into the cluster. So the last thing I want to do is I want to actually play with quota. And oh, look at that. I have one of my OTP things got appended here on accident. Okay, so let's talk quota, because and this is something I didn't have a chance to pre-flight before we went ahead and did this stuff. But let's go through, and we're just going to actually do a memory and CPU quota. I want to go new file, quota.yaml. And so again, these are the sum total across your entire namespace. These things are applied to a namespace. How much quota do you have to work with? And so what we're going to say here is we're going to say, well, I'm going to give 10 gigabytes of requests and 20 gigabytes of limit, and 1 and 2. Let's do 2 and 4 CPUs. Okay. And so we'll go ahead and we'll set that, and then I believe. Yeah, so we'll go ahead and we'll create that quota. So cube control apply -f resource quota.yaml. Mem CPU demos created. Cube control get quota. And you can see here what we get is it's a descheduler. Is it called rescheduler, descheduler, defragmenter? Yeah, so that's a good name for it. And the naming there has actually been changed. It was called rescheduler at some point, but the truth of the matter is that you don't reschedule pods. What you do is you kill them, and then you let sort of the replica set or something above you actually go ahead and create replacements, and you can actually place those replacements someplace. So there's this subtlety in terms of pods, once they land on a node, live and die on that node. And so that's why that name has been adjusted over time. Okay, so what we look here is we can say, oh, look, we have hard limits, and then the status actually shows what our limits are, and then it shows how much we've actually been used. And once I instituted this quota, let's go ahead and see what happened to my cluster. I'm going to go through and look at pods in the default namespace. Look at all the pods. And you can see that I'm running 5 of the 2 GB limit ones, the guaranteed ones, and then my best effort ones are running, continue to run. If I look at my deployments, let's see. Oh, I only specified 5 of these things, right? So let's go ahead and let's up the number of guaranteed ones and actually see what happens. So I specified 5. Let's try and run 6 of these things. Keep control apply -f -d g. So the system accepts it just fine, but what you're going to see here is that it's going to be like I'm running 5 and I don't see any pods scheduled, right? So this is actually a different failure mode, right? Before, when I ran out of quota or when I ran out of space on a node, I would actually the node would say, hey, like, I have this pod, I'm trying to schedule this pod, but I can't schedule that pod. The way quota works is it works at the admission level. And so that means that I set my deployment to say I want to run 5 of these things. But the deployment, and then the deployment actually configures, it says, oh, 1 unavailable, right? And so the deployment continues to actually try and make it work, but every time it tries to create a pod, it's actually going to get rejected. And if you go and if you look at it ends up being the replica set for the thing. But let's go ahead and we'll do that from the command line. Cube control get describe deployment quota G. I can go through, okay, we scaled this thing up, but it has a condition on it, right? It says replica failure true, it failed to create. So, so it wasn't able to actually create one of the replicas that it needed to create. And so now if I do cube control describe replica set, and I'll go through and I'll name that thing. Then what we see here is here's the error that we got. So like I tried to create this particular pod. It was forbidden because I exceeded my quota and the name of the quota, and it says, well, I requested 2 GB of memory, but I'm using 10 and my quota is 10. And so this is telling me that I'm out of quota. And so when I'm out of quota, I can't even get new pods into the system. Like there's essentially a door saying I can't do that. Sorry, I'm just not going to even let these things in. And then one of the other things that you'll see here with events and is that when it writes this thing out, it actually doesn't actually say the full name of the pod, and it does this so that it can actually you don't see spammed events. So this will actually sort of like retry this for a while because hey, I might go through and actually adjust my quota, and then I'll have this thing show up. So let's go ahead and do that. Let's see what happens there. Let's say I'm like, oh man, I'm trying to do this. Hey, administrator, give me more quota. He's like, all right, I'll give you more quota. So we'll actually go through and I'll give you more requests. We'll apply that quota. All right, so now we updated the quota. And now if I describe this replica set, oh, look, it retried it again. It got to the point that it's working now, and now it's all up and running. So yeah, so now there are, like if you're running a node autoscaler, the idea of like cluster autoscaling might be, hey, I'm trying to schedule pods, but I can't schedule pods. What do I do, right? And so you'll see that, hey, these pods are unscheduled, or I need to add more nodes so that I can schedule those things. Quota is a different thing. It's a policy thing, right? I want to control the cost of how much this namespace can use in terms of resources. One of the things that you can do, and there's folks looking at systems like this, where they'll automatically adjust the quota based on some sort of larger idea of quota. So it's like, hey, I'm trying to use this quota, and I'm trying to actually do this thing. I don't have enough quota. Can I get more quota? And maybe it'll be like, oh, well, you have a set of namespaces. What I'll do is I'll automatically move from some of your quota from this namespace where you're using less of it to this other namespace. Or you can build systems on top of this that can automatically help adjust quota. There's a few things that people are toying with there. I haven't seen anything really dramatic in terms of people building dynamic quota adjustment systems. So finally, the question is, well, what happens when I actually reduce this quota again? So now I have 6 of these things running. Let's go ahead and reduce the quota. does it actually go through and kill things? Right, deployments, I have this thing. No, everything's still running. So quota is an admission time thing. It's when we actually let things get into the system. It doesn't go through and actually kill things after the fact. But if I were to actually go through and let's see one of my pods fails. So let's go find one of these things and I'm going to go through and delete one of these pods. What you'll see is that the deployment, unfortunately, can't get a replacement up and running because the quota has been reduced. So it's one of these things where you're grandfathered in, but if you try and do a new deployment, if you try and do a rolling update, that churn will actually lock you down at a lower level. So yeah, so one of it unavailable. Here we are, it is what it is. I got 5 of them. I can't run the 6th one because there's 6 desired, but I'm getting an error because of quota. Yes, that's how it works. Now, the other thing here is let's go through and we're going to do something else that's fun. Cube control, delete, QRD, best effort. So we're going to go ahead and delete our best effort set. And then let's try and like recreate this. So now if I look at my deployments, my best effort, none of these guys are running. Now it turns out that, well, let's see. Yeah, none of these things are running because once you have quota on a namespace, everything that you put into that thing has to have some type of limit. So if you want to make sure that you at least have some limit on stuff, you can go ahead and do it with that. And then finally, and we're not going to have enough time to actually play with it, there's this extended system called limit range. And this is an extensible admission controller that you can enable. But to do this, so here we go through and you can do create namespace, a default mem example. You can do a limit range. And essentially what you're going to want to do is you're going to want to, you have a default limit and a default request for memory. And if you actually try and submit something that's under best effort, it'll actually stamp these things onto it such that you at least have a minimum there. And so this is a way to sort of set your default policy for these things. And let's see, so this is, yeah, so there's a bunch of detail here. I haven't had a chance to play with this, to be honest. But this is the thing if you want to go through and limit or set defaults for your request limits. So that hopefully gives everybody a good grounding on this stuff. I'll put my sort of like notes here that I have up in a gist, and I'll add that to the description in the YouTube video after this is all said and done. Let's see, other things that are interesting here. Oh, I just want a couple other things. Is there's the node itself, the kubelet has its own behavior in terms of like it wants to actually keep enough room for the system itself to be doing it. So like when I actually go through and I look and I say, show me this node, and this node reports, hey, look at me, I have 15.67 gigabytes available, right? Where does that number come from? Well, it turns out that the kubelet can look around and actually detect how much RAM, and then there's a and then it actually applies some guesstimates in terms of how much room does it want to actually keep around for the system itself, right? So how much of that, if I have 16 gigs of RAM, how much of that do I want to actually give to Kubernetes versus how much do I want for the kubelet, systemd, SSHD, all that other stuff. And so, and then the question is, well, if too much stuff is running, what does it start killing to actually maintain that amount of RAM? So that's actually interesting also. So there's a whole bunch of flags and soft and hard eviction and sort of the amount of grace period and stuff like that that you can adjust in the kubelet. So there's a lot of tunables here with this stuff. So yeah, so that's it. Any last questions before I go about this stuff? Again, I'm not an expert here. I do have quite a bit of sort of experience and understanding, but like there's a ton of detail here. This is actually more complicated than it might first appear. So any last questions before I go ahead and sign off? If not, I will wish everybody a great Thanksgiving if you're in the U.S. If you're not in the U.S., have a good weekend. I'm going to be off next week, and then the week after that is AWS reInvent, and then the week after that is KubeCon. So I have like a busy 3 weeks coming up. So I probably won't have a TGIK until after KubeCon, unfortunately. I've been trying to find somebody who might want to do a guest spot on this, but it's you got to do a little bit of tap dancing to do this type of stuff that I'm doing. So I'm not sure I can get anybody to sign up. But if not, everybody have a great weekend, and feel free to ask questions after the fact in the comments on the video that we're going to post. I definitely keep an eye on those. All right, see you all later. Thank you for watching.